Good afternoon, everyone. Welcome back to the afternoon session. Today, it's a great pleasure for me to introduce Professor George Zweig. Interestingly, George has a connection both to the eponym of the conference, which he knows, but also to the current announcer, which he does not. George did his PhD from Caltech with Richard Feynman, although Gell-Mann is on record saying that he was George's advisor and Feynman signed his thesis in his absence. Anyway, later George moved on and became the lab fellow at the Los Alamos National Laboratory, a place where I spent some of my most productive years before moving to Singapore. Very tenuous connection, but one nonetheless.
Good, well, thank you.
Just let me say a few words about your work. Right after his finishing his PhD, he developed the ideas of quarks, which he called ACEs, independently of Gell-Mann. And his contribution subsequently has been phenomenal. He was nominated for the Nobel Prize by none other than Richard Feynman. And although he did not win, his work is universally acknowledged as being crucial to this field. Later, he moved on to neurobiology and worked on the transduction of sound to nerve impulses in the cochlea. And as if that were not enough, since he thinks life is boring without work, in the 2000s, he made his foray into Wall Street, joining and co-founding two quantitative hedge funds. A stellar career, and we look forward to hearing from him his memories of Feynman. Thank you.
Beware of autobiographies because of their inherent conflict of interest. This is what I learned as I was growing up from my uncle, who was a psychoanalyst. So you and I have a problem, because the only original things I have to say about Feynman deal with my interactions with them, and so they carry all the risks of autobiography. I have an old friend, his name is Cormac McCarthy, the writer, and he once asked me if he should write his autobiography, and I said, only if you tell the truth. Now, when Lars asked me to talk here, I was very, very reluctant. And I think in an email to you, I said, talking about Feynman would be almost as bad as talking about my father in public. And it's true. It's true. So I eventually agreed. And following my advice to Cormac, and with my uncle watching, I will try to do justice to the man who meant so much to many of us. Well, in the 1950s, two of the most interesting and unsolved problems in particle physics dealt with the strong interactions and also developing a quantum theory of gravity. Feynman at that time believed that not enough was known about the strong interactions in order to start to tackle that problem. And quantum gravity was very, very difficult. You might wonder why a man who was interested in fundamental physics would work in superconductivity. And that was because he believed that there was a good chance that the phenomena that was observed, in fact, was inconsistent with quantum mechanics. And that by studying superconductivity, he would be able to, I think, revolutionize that field and get a deeper understanding. That understanding came, but from quantum mechanics, as he showed. A few months after I came to Caltech as a graduate student, he started to work in biology, and I think he just sort of punted. He said, it's too hard, I'm going to do something else. I don't know, that's a conjecture. But in any case, he came back after a year, and I talked to him at that time, and he said that biology was interesting, but he was really wasting his talents. What he also told me a little while later, and now he was really excited, was that he was going to renormalize gravity. He's going to do it. And the way he's going to do it is going to put pressure on himself, and he's going to teach a class. And I attended that class. The first day of class, Feynman asked, suppose Einstein had never been born. How would the particle theorists deal with gravity? What would they do? Well, they would say, there's got to be a particle that's responsible for the force. And he called that particle the graviton. The question then was, what are its properties? Well, it's a long-range force, so it's probably going to have zero mass. Now, the next question was, what is its spin? So we argued that particles that are exchanged that have an odd spin, like 1, 3, 5, and so on, have the property that likes repel. And so that's not going to work. So it's got to be on the even series, 0, 2, and so on. So the simplest possibility was 2, but he said that, gravity, mass, and energy are equivalent in some sense. So if you had 2 teapots and you were measuring the gravitational force between them, as you heat the teapots up, they should be more strongly attracted. And a spin 0 particle won't give you that phenomena. So the simplest possibility was spin 2, and that's how he ends the lecture. The second lecture, he comes in the room and he's full of energy, and he goes to the upper left-hand corner of the blackboard, and he starts writing down the rules for quantum gravity. Feynman rules for quantum gravity. It's like Moses, There it is. He then proceeds, as the first calculation, to imagine that that Mercury and that the sun were elementary particles. And he calculates the scattering of Mercury off the sun, and in a 50-minute hour, he computes the advance of the perihelion of Mercury, gets the answer, which is twice that Newton had found and that had observed to be correct. I would say that was the most incredible display of intellectual prowess I thought that I would ever see, and I knew it at the time. It was unbelievable. Now, there was no curvature of space-time. There were no Ricci tensors. There was no Christoffel symbols. He just went and he calculated the damn thing. I had taken a course from H.P. Robertson, a grand old master of gravity. In fact, Robertson in 1936 received a paper by Einstein. He was a referee for that paper. The Physical Review received the paper. And in that paper, Einstein supposedly showed that gravitational waves do not exist. So in response, in the referee's report, which was longer than the paper, Robertson, in fact, shows that they do exist and how strong they would be. He worked the whole damn thing out. I have been told that Einstein, when he received the review, was absolutely furious. Absolutely furious. I don't quite understand why, but this is supposedly true.
He told the editor that he didn't send it to him with thought that he would share this paper with somebody else before publishing.
I see. Kurt said that he thought that the paper would be published and not shared with someone else before publication. In any case, Einstein used H.P. Robertson's work, put it in a revised form for the paper. He indicates in the paper, which I just recently read, that he thanks Robertson for pointing out some error, some minor error. And he submits the paper not back to the Physical Review, but he submits it back to the Journal of the Franklin Institute. In any case, I took this course in gravity from H.P. Robertson. And it started in September, and it wasn't until March that he computed the advance of the perihelion of Mercury. So in that period of time, I was taught what Feynman didn't need to know to compute the advance of the perihelion of Mercury. Now, things got difficult because a graviton couples to the stress energy tensor, the spin 2 particle. And the graviton itself has energy. So the graviton couples to itself. Light couples to charge, and so it doesn't couple to itself. And this self-coupling created enormous problems. Now, Feynman's lectures were transcribed by a graduate student. He had the office next to me. Bill Wagner was his name. And I remember him dragging me in to his office and turning on the tape recording of the lecture that day. And it was incredible. I mean, there's this charisma and this dynamism, but the English is all over the place. And as it says here, it promises infinitely less intelligence than it delivers. It was really unbelievable. And he was beside himself. He didn't know what to do. And you might recall that the Feynman lectures in physics were edited by 2 full professors who were very good. And it was a horrendous job. Now, the course continued throughout the academic year. Feynman struggling with one problem after another, and it ended on an unsatisfactory note. Of the 27 lectures that were written up, only 10 were distributed to the students. Only 10 were, so to speak, published. And I noticed a dramatic change in Feynman's demeanor before and after. I think it had a profound effect on him. It sort of took the edge off of him. And really, this talk is about his process of recovery, which took a period of maybe 6 years or so, and what we can learn from that. Well, I wanted to be a theorist. I majored in mathematics as an undergraduate, and I went to Caltech hoping to be a theorist. But, you know, it was fairly intimidating. The atmosphere is fairly intimidating. And I realized something which I think is important for the young students here that want to be theorists. And that is that when you start in graduate school, you don't know enough theory to do anything that's interesting. So the thing to do is go over and for a couple of years at least, do experimental work. You'll never have a chance to do that again, and you may even end up liking experimental work. So that's what I did. There was a man called Alvin Tallestrup, and he was professor of physics there, and he had this idea that the future in physics lay in doing experiments at other accelerators. Caltech had a synchrotron, the highest energy electron accelerator that existed at the time, but he thought the future would be elsewhere. And so he was going to do an experiment at Berkeley, at the lab there, at the Bevatron, and he had a K-beam that he was going to use to look at K goes to 2 pi plus gamma, and I thought if you look at K mu 3 and measure the polarization of the mu out of the plane of decay, you can see if time reversal symmetry holds. So I spent a couple of years doing that, and actually ran and got some results, and a preliminary scan didn't show an effect, and then I had this choice of like spending 2 years doing careful analysis and finding out exactly what the upper limit was for time reversal violation, or doing something else. And that's when I switched to theory. So the natural theory advisor was Murray Gell-Mann. So I went in to see Murray, and I asked him, would you be my thesis advisor? And instantaneously he said no. And then there was this silence. And then he said, I'm going to the East Coast on sabbatical, but I'll talk to Dick. And Dick is Richard Feynman. I would have never had the guts to go in and ask Feynman to be my thesis advisor. Just no way. And you know, and in fact, I postponed going in and talking to Feynman as long as I thought was possible. But I eventually did go in, and I asked him to be my thesis advisor. And he became very official. His pitch of his voice lowered, and he says, Murray says you're okay, so you must be okay. And then he told me about his time with Wheeler, when he went in to see Wheeler and asked him to be his thesis advisor. And Wheeler told him that he should come in once a week. They would discuss physics for an hour and then adjourn. So the first time Feynman came in there, they started to talk, but Wheeler took out his stopwatch, clicked it on, and they spent their hour. The second time that Feynman went in there, Wheeler took out his stopwatch, clicked it. Feynman took out his stopwatch, and he clicked it. And that's how the second meeting began. In any case, Feynman explained the rules to me. He said, I want you to come in every Thursday at 1:30, and we'll talk about physics from 1:30 until 4:15, when we will adjourn for tea, and then at 4:45 we'll go to the physics colloquium. So every week I worked like crazy preparing for that meeting because I didn't want to bore Feynman. And I never talked about the same subject more than once, even my thesis. One day I went in, this is my thesis. Very good, and that was the end of it. Now, there was a particular meeting which I wanted to talk to you about today, where I went in and now I was very excited, and I had just read a Physical Review article that provided additional evidence that a particular meson, a particle called the Phi, exists. And as you see over here, as I orient this, as you see over here, that paper showed that a particular particle called the Phi goes to K and its antiparticle, but doesn't go to another couple of mesons, a rho and a pi. And you'll see in a moment that this is actually astonishing. Now, the next couple of slides, the students that are not experts don't need to worry about, don't need to understand. The thing you need to understand is that something that's supposed to happen doesn't. Okay? But for the experts, I'll show you one of the experimental results. So what you see here is the reaction K minus plus P goes to lambda plus K bar. And here you have what's called the Dalitz plot. One axis is the mass squared of the KK bar system, and the other is the mass squared of the lambda K system. And you see that there are many, many events that have a particular mass squared of KK bar that indicates that this is a resonance. They come in different charge combinations, and that's what this cross-hatching means. There isn't any resonance over here with lambda K. If you project that, you get something that's smooth. Okay, well this is fine. This is what you might expect, except if you know a little bit about physics and you are an old-fashioned physicist where you actually calculate things, you'll notice that it's very strange that you have all of these events that are piled up close to this line what this line means is that points inside are consistent. They are consistent with the conservation laws. Whereas if you're out here, for example, then it would indicate that the event violated, for example, the conservation of mass. So they're all piled up here at the edge of phase space, and the K and the K bar come out in a P wave, and so you get suppression at the edge of phase space, but that's exactly where you have all these events. Okay, the next graph shows what happens if you look at the 3 pi's. So what we have over here is, again, K minus P goes to lambda, but now 3 pi's. Now, the reason why you might think you get a lot of events here is because you might think that this particle, the phi, goes into a rho and a pi, and then the rho decays into 2 pi's, so that you would see a lot of 3 pi events at the mass of the phi, which is over here, and there's really no statistically strong evidence for it being present. So the authors of the paper, who are, by the way, very respectable, like one of the authors, Nick Samios, became the director of Brookhaven National Laboratory. So these were professionals. They write, the observed rate for phi goes to rho pi is lower than predicted values by 1 order of a magnitude. However, the above estimates are uncertain by at least this amount, so that this discrepancy need not be disconcerting. Well, I was extremely disconcerted because the number of rho pi's compared to KK bar should be 4 times as many. So you should see 4 times as many of these as you saw in the previous plot for these. But in fact, if you look at what's observed, at least 35 times more KK bars were present than rho pi's. So the suppression was not 1 order of magnitude, it was 2 orders of magnitude. Now, this is the strong interactions, and I had learned from Feynman that in the strong interactions, everything that possibly can happen does, and with the maximum strength that's allowed by unitarity. And this calculation reflected that. But that's not what happened. So the only way you can get suppression is if you have a symmetry, but there's no symmetry here, or if you had some new dynamical mechanism. Now, Feynman was not disconcerted. I mean, he went into a tirade about how long the experiments are, and you shouldn't worry about them, and don't pay any attention. And he used unitarity in a different way. He says unitarity mixes all states with the same quantum numbers. So unitarity would mean that the rho pi and the KK bar would be exchangeable with one another. And so a suppression is absolutely impossible. Okay. Now, the next time I saw Feynman was at the Erichi Summer School. And he was talking about SU3 symmetry and the weak interactions. And I found it rather remarkable because, I mean, he's a teacher and he would teach the usual material, but in a summer school like this, you would think he would be somehow talking about his original work rather than the work of others. In any case, 6 months had passed since Murray published his quark paper and since I had my 2 CERN preprints circulated. And by that time, I'd come up with the explanation for why the phi doesn't go to the rho pi. And so now the students can come back and I think hopefully understand what's being said. So I assumed that the strongly interacting particles are made from some fundamental constituents that I called aces. And the word ace comes from the Latin word meaning a unit. I only needed 3 particles, or 3 aces, to explain the existing particles, but there were 4 leptons. And I thought there should be some kind of correspondence between the fundamental particles in the weak interactions and the fundamental particles of the strong interactions. So that was another reason for calling them aces. I should have called them dice, because eventually 2 more leptons were found, and then once again 2 more aces, or quarks as they were then called. In any case, the idea was that you take a pi and you make, oh, by the way, this notation was such that these objects, I use the same symbols for proton, neutron, and lambda, because unlike the proton and neutron and lambda, these had baryon number of 1/3, used 3 of them to make a baryon, but they had the charges of a proton, neutron, and lambda if you just add a minus 1/3 to all of the charges of the ordinary particles. In any case, the rho plus was made out of a P0 and an N0 bar, where the spins would cancel. These were fermions. The rho was the same combination, it's just that the spins lined up, and so that meson had spin 1. The K was made out of the K plus, just like the pi plus had a P0, but instead of an N0, it had a lambda 0 bar. The phi was just made out of lambda 0 bar. Now, if you look at the baryons, the lambda is heavier than the proton or the neutron. So I assumed that the lambda 0, in fact, would be heavier than these 2, and we'll talk about the masses in a moment. But now let me tell you what the explanation was for the suppression of phi decay. Here we have a meson. It's made out of an ace and an anti-ace. And the rule was, the dynamical mechanism that suppressed the decay was that the constituents in the initial state would flow to the constituents in the final state. So if you started off with a phi, and this would be a lambda 0 and a lambda 0 bar, in the final state you'd have to have a lambda 0 here, and then a lambda 0 bar here, which is true for the K and the anti-K, but it's not true for the rho and the pi. So there were a lot of other bonuses for thinking this way. If you said that the mass squared of, say, particles in a particular group, an SU3 representation, had some common mass, and then the sum of the masses of the constituents minus some energy of interaction, if you neglected this, then you get the result that the rho and the omega would have the same mass, and at that time they were approximately the same. And the K star would be lighter than the phi because it didn't have, this had 2 lambdas and this only had 1, where this had 0. And if you were to have averaging relations for these, you'd end up with relations like this, that the mass squared of the phi is twice the mass of the K star minus the mass squared of the rho. And you know, there isn't any other way of getting this kind of order. The point of this is that these objects had dynamics. And the question was, you know, are these real? Now, you don't really know whether they're real, but it's not clear what it would mean to have a rule like this if they weren't real. It's not clear what it would mean. You don't see this here, but the way you get the hadronic spectrum is you start letting the aces orbit around one another, and when they orbit around one another, you have a coupling between their angular momentum and their spin, and that leads to mass splittings, which look like they're right. So a fictitious object is not supposed to have angular momentum. So we didn't know whether they were real, but the dynamics sort of told you that they were real. Now, Feynman, when I explained all this to him, he hadn't changed. He just said, the experiments are wrong. The experiments are wrong. He also believed that, part of what people called the bootstrap. He believed not necessarily that all the particles made one another the way that people were calculating them, but that there was no such thing as a fundamental hadron. And both for philosophical reasons and for reasons that related to his experience, where when he proposed V minus A, all the experiments were against him. For both of these reasons, he just thought that the idea was crazy still. By the way, Li and Yang said, oh, the experiments are right. And they said that the weak interactions is not vector and axial, they're scalar and tensor. And they were wrong. So it's a tricky thing to look at experiment and understand how to deal with it. So that raises the interesting question, which is important for people that are going to do this and haven't already formed an opinion. What constitutes the craft of theory? Feynman tells you what it is in one of the lectures that he gave, the last lecture at Cornell. This is in November. So this is like almost a year after we have aces and quarks. He says, in general, we look for a new law by the following process. First, we guess it. Then we compute the consequences of the guess to see what would be implied if this law that we guessed is right. Then we compare the result of the computation to nature with experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it is wrong. And that simple statement is the key to science. It does not make any difference how beautiful your guess is. It does not make any difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it is wrong. Now, he goes on in these lectures later on and spends a lot of time talking about how you make the guess. And never once does he say, you look at experiment. Now, it is true that at least in one case, and this is the only case I can think of, that someone understood something about fundamental physics without looking at data, and that was Dirac. And Dirac was Feynman's hero. But all the other cases, it goes a different way. In all those other cases, what you always have is experiment at the beginning and experiment at the end. Planck, when he quantized the radiation, knew what black body radiation looks like, and he tried to explain it. Rutherford, when he scattered alpha particles off of gold and found the alpha particles coming back at him at a rate which was not expected according to current theory, he used that to develop his Rutherford model of the atom, where the charges, positive and negative charges, were separated from one another. Bohr looked at all those spectral lines and organized them. And even Feynman, when he wrote down his theory for V minus A, used the fact that parity was violated. There he had Dirac's equation for the electron. He made it massless. And then the problem was, how do you do it so that you violate parity? And you get his equation for the massless neutrino. I came across a very interesting article that David Goodstein wrote. David Goodstein, at this time in 1960, I'm sorry, this is going to be 1960, yeah, it's right after the Nobel Prize. Writes, he was a young professor of physics at Caltech, an assistant professor, and Feynman was going to give lectures at the University of Chicago. And he was staying at the Quadrangle Club, which is their club for visitors. And Goodstein and Feynman shared this suite. And Goodstein then wrote up his recollections of that time with Feynman. And he says, in the immediate aftermath of his Nobel Prize in 1965, Feynman suffered a brief period of dejection, during which he doubted his ability to continue to make useful, original contributions at the forefront of theoretical physics. I might also add that after his failure to quantize gravity, that's when he really, in earnest, started doing things like drawing and having other kinds of interests that I think consumed his attention. And evidently, according to David, the Nobel Prize made the situation even worse. Now, when Feynman was at the Quadrangle Club, sitting in the lounge there, he started to talk to Jim Watson. And Jim Watson had a manuscript. And he asked Feynman to read it. And Feynman actually read it. And when, I guess this is now in 67, when Dave Goodstein came back into the suite, Feynman said, "You got to read this book." "Sure," I said, "I'll look forward to it." "No," he shot back, "I mean right now." And so, sitting in the living room of our suite from 1 to 5 in the morning, with Feynman waiting impatiently for me to finish, I read the manuscript that would become the double helix. At a certain point, I looked up and said, "Dick, this guy must be either very smart or very lucky. He constantly claims he knew less about what was going on than anyone else in the field, but he still made the crucial discovery." Feynman virtually dove across the room to show me the notepad on which he had been anxiously doodling while I read. There he had written one word, which he had proceeded to illuminate with drawings as if he were working on some elaborate medieval manuscript. The word was disregard. "That's what I'd forgotten," he shouted in the middle of the night. "You have to worry about your own work and ignore what everyone else is doing." At first light, he called his wife Gwyneth and said, "I think I figured it out. Now I'll be able to work again." So that's February of 67. In September of 67 to May of 68, Feynman taught a course on particle theory. He was getting back into it. He's going to teach a class and that way find out what's going on. After he finished that class, I bumped into him as we were both going to the Greasy, which is the Caltech cafeteria. And he was very excited. And he told me all the things that he had worked on. And then he stops, and I stop, and he looks at me, and he said, "Did I miss anything, Zweig?" And then, for God knows, I don't know, I just, once again, told him all about ACEs. And this time, he was quiet. And when I finished, he hitched up his pants like that, and he says, "I'll look into it." Now, what happened next, evidently can be discerned from one of his notebooks. Evidently, on the 19th, let me get this straight, on the 19th of June, writes his biographer here, Feynman began to think of each hadron. So this is like 3 weeks after I talked to him. Began to think of each hadron as a collection of smaller parts of unspecified quantum numbers, which he christened partons. He thought of partons as arbitrary, bare ideal particles, the quanta of some underlying field, their exact number in any hadron being indeterminate. All right. So that was the beginning of the parton model. That had nothing to do with quarks, because he's just talking about scattering, and the results of those experiments aren't sensitive to whether the quark has or the parton has baryon number of third. But he had a second road, which is the road to ACEs or concrete quarks. And is Finn Ravendal here? Finn was supposed to come. He didn't come. So Finn was a graduate student that had just come to Caltech, and he was he was sort of surprised that no one was working on what was called the quark model. Murray wasn't, I wasn't. I was starting to transition over into biology. But in any case, Finn was interested, and so he was working on it more or less by himself, and Feynman heard about it. Oops, I'm sorry, this is not good. And as Finn writes, one day in the fall of 1968, Feynman was suddenly standing in the door to my office, smiling broadly, as he often did. He wanted to know everything about the quark model I had used and the calculations of strong and electromagnetic decay amplitudes. It sounded like he had never heard of quarks before. So he worked with Finn and also another graduate student called Mark Kisslinger for about 3 years. And in 1971, he published the result of their calculations. He was basically looking at reactions that involved strongly interacting particles, but also a photon. And they computed 75 matrix elements, and they've compared them with experiment, and they published the paper. So this is 1971, and I was working over in the biology department, and I remember coming back to my office. And as I was walking down the hall, I see Feynman, and he's on the far side of the hall, and when he sees me, he breaks out in this enormous grin. And then he starts splaying, his fingers are splayed apart, he's walking like this, right up to me, and he says, "Congratulations, Zweig, you got it right." So you have to love a man like that, I must say. In any case, in 1977, Feynman nominated Murray Gell-Mann and also me for a Nobel Prize. And the reason I'm mentioning it is that it shows you how magnanimous Feynman is.
George, must be 67.
Pardon me?
Must be 67, right?
No.
1977.
Murray had the prize already, 69.
He nominated me for a second one.
Oh, the second.
For a second one. That's what I'm telling you. Feynman is really a generous man. I mean, he didn't have 2 Nobel Prizes. But, not only that, Murray was always, sticking the knife into Feynman. Anytime he had a chance to goad him, he would do it. And I remember one morning, I come into work, and I bump into Feynman, and Feynman is just, he's really upset. I've never seen him like that before. And he tells me that he was over at Murray's house the night before. And Murray has this grand piano. And Murray drags Feynman over, and he starts hitting these notes on the piano. And said, "What is this note? What is this note?" And he knew that Feynman was tone deaf. He just didn't hear tones. And he just kept asking him, and evidently it finally got into Feynman, got under Feynman's skin. And if you often, or if you ever wonder about why Feynman plays the bongo drums, okay, so other sides to Feynman.
What are those numbers?
Oh, yes. I often wondered why it is that it took me so long to get Feynman to believe that there are such things as aces, or fractionally charged constituents. And in some ways, Feynman was right. At the time that I wrote the CERN paper, there was a definitive compilation of mesons. It's like the Berkeley, I don't know whether the Rosenfeld tables, I don't know if people know, this is the definitive compilation. And it was published in the Reviews of Modern Physics, which for the students is like, it's the most respected journal where you put the results of calculations that are believed to be correct. And at that time, in the publication, there were 26 mesons that had been measured. we now know that of those 26, 19 don't exist. And 7, you can't make out of QQ bar. If they existed, then the idea of aces would not be correct. So he's right. Experiments very often are wrong. And by the way, the reason it was so terrible, I mean, you say, well, don't these experimentalists know what they're doing? Yes, they do, but they were using a new technique that was not well understood. They were using bubble chambers. And people that didn't find things didn't publish. And they got other people got statistical fluctuations, and they published. In any case, he was right. So you might ask, well, what did it take to weed through all this mess? And I think a theorist has to be trained in experimental physics, so he can read every one of some 200 papers and decide whether or not they think a particular result is really meaningful. So I had that training, and I read the papers. You have to have the patience to do that. You have to be really driven. So I think there may have been something else going on. You see, it wasn't just a matter of figuring out which mesons existed and which didn't, because that you can do by using symmetries. The crucial point was that the phi did not go into rho pi, and I guess I should have mentioned this before. Let me just go back up here. Yes. Yeah. The whole point really is that there was something that was supposed to happen that didn't. It was an anomaly. I mean, there was nothing else like it. And that was a suppression of rho pi, and that suggested the existence of aces or concrete quarks. Concrete quarks are quarks that are real particles and not hypothetical. And then the even greater suppression of another decay of a particle called the J psi. That was made out of the fourth quark and its anti-quark. So the phi was lambda 0 bar. This is B bar. And this you would have noticed in the phi goes to KK bar case, if the K had any more mass than it did, it wouldn't decay at all, and the phi would really be narrow. So in this case, mesons with a B in them or a B bar were just too heavy for this particle to decay into them. So the observation of the suppression of this decay of this particle almost a decade later confirmed the existence of quarks. I mean, quarks were really discovered by looking at phi goes to rho pi. So the question is, why didn't Feynman latch onto this? Here's an anomaly, and you got to study it. And this is a conjecture on my, this is a conjecture on my part that it might have had something to do with superconductivity. Now, this is just a wild conjecture. But Feynman saw an anomaly. He saw superconductivity, which was absolutely bizarre, and he hoped that it would lead to something else. So in any case, he was right to distrust experiments without actually careful analysis, and it isn't his style to do that kind of analysis. So there were other sides to Feynman, and I'm glad that Michelle isn't here. What I call a dark side. So often he says what he thinks and he does what he pleases without any regard to the effect that it has on other people. I had a friend while I was at Caltech. Her name was Jenny Joy LaBelle. She was a young assistant professor of English literature. She was very attractive. And LaBelle told me this story. And she also told the story to the Caltech a historian. They had people going around interviewing people at Caltech, asking them about what their life at Caltech was like. And this is what she wrote, which is exactly what she told me. Nobel says, I was going to a meeting in Bridge Laboratory of Physics, the building that he taught in. I was walking up the stairs and I heard this voice say, come back down the stairs. And I went back down and I said, why did you want me to walk down? And he said, so I can watch you walk up the stairs again. I suppose I was wearing a miniskirt, which is what I tended to wear in those days. Then he said, I'm Richard Feynman. I certainly knew the name, but I didn't connect him with the man in the white shirt and the gray slacks. But I laughed and he laughed. That's how I met Feynman. And then Jenny Joy goes on to say, I found this great quotation. Do you know Ilka Chase? She was a novelist and actress in the 1920s and 1930s, and she was in the Bette Davis movie, Now Voyager. This wonderful quotation, where at one point she said, George Moore unexpectedly pinched my behind. I felt rather honored that my behind should have drawn the attention of the great master of English prose. So I thought I would say that I felt honored that mine had attracted the great quantum electrodynamics master. And then she goes on and says, perhaps it was Oscar Wilde who defined flirtation as attention without intention. Now, not all women would be able to protect themselves with such savoir-faire. I'll just relate one other incident. Murray had a graduate student who was going to graduate. His name was, I'm just going to make up a name. His name was Bob. And Murray came up to me and said, I'm going to be out of town. Could you be the chairman of Bob's thesis committee? And I said, sure. Feynman was on the thesis committee. Bob had a very unusual thesis. He was working in a toy field theory. Murray worked in toy field theories. Murray's theories had 3 dimensions and 1 time, but no interactions. Bob's theory or thesis had fewer spatial dimensions, so it wasn't realistic, and time. But he worked with interactions, and so he could find certain properties of the theory which were interesting. And for some reason, it just got to Feynman. There was nothing wrong with the thesis. There were no mistakes. Feynman just didn't think it was a subject that one should give a PhD thesis in physics to. And so when the exam was over, Bob answered all the questions. I asked Bob to step out of the room. Feynman refused to sign the thesis. And he said, he should go back and write another thesis, write a real thesis. Now, Bob had been there, I forgot whether it was 4 years or 5 years, and there's just no way that you're going to ask him to do that. And everybody else was satisfied with the thesis, including his advisor. So I tried to reach some kind of compromise. So in the end, Feynman said he would sign the thesis if Bob would address a list of questions that Feynman would draw up. So, we called Bob back in and told him what the situation was, and he was just devastated. He then worked for a period of, the questions could have been answered in a month or 2, but Bob just didn't feel like working. He was like paralyzed. He eventually dropped out, didn't get a PhD in physics, and then went on to medical school. Yeah. I tried to get Murray to intervene, but evidently he wasn't able to. Well, Feynman was fiercely independent. And there is this rumor that Johnny von Neumann was envious of von Karman. Both of them were Hungarians, because von Karman had invented consulting. Now, Feynman, in fact, did consult. He made heavy use of consulting, and he used it to buy his independence. I, at one point, by accident, saw his salary. And, you know, there were many people, or so, I don't know how many, but there were quite a few people in the physics department that had a higher salary than he did. And one of the reasons, and probably the main reason, the only reason, is that he didn't want to go on the DOE contract. He just didn't want to bear that constraint. He was truly independent. And, you know, he would, I think he viewed the physics, the theoretical physics community as just a bunch of cogs in the wheel. So somebody that practices theory writes a paper. All the other theorists go and look at it. Aha. And then they go and they take the results and they put it into their paper, and then they publish their paper, and the wheel goes round and round. And he had this saying, you know, like a pack of hounds, the theorists chase one fashionable problem after another. So he avoided it by consulting. And I think he believed this. He never said it. It's the same thing that my mother believed, and she never said it either, and that is, you work to please yourself and not to please others. Remember that, students. He was also quite honest and truthful, and there was really no one else that I knew that talked to so many people about so many subjects, and they always heard the same story. And that reminds me of the story of Sam Rayburn. Sam Rayburn was in the House of Representatives in Congress in the United States from 1913 to 1961. Lyndon Johnson was his protege. When Sam died, he was living in a small Washington hotel room, and his estate was valued at $30,000. And a reporter once asked him, "You talk to so many people about so many things. How can you keep your story straight?" "I tell the truth," is what Rayburn replied. Okay, education. When I went to grad school, I had another person who was there at the same time. His name was Harvey Shepard. And Harvey wrote up a conversation that he had heard at one of these Thursday 4:15 teas. Harvey says, "One day during afternoon tea in Bridge Laboratory at Caltech, Feynman was talking to a group of graduate students. He asked us what research we were working on. And after several responses, he said, 'Doesn't it bother you knowing that others are working on the same problems, using the same approaches? I can't work on something unless I believe that I am doing it in a different way from everybody else.'" I'm not sure what that means. Well, there is an interesting question, which in fact I'm going to ask people in the audience that had some interaction with him. What was his influence on me and his other students, and more generally the world in large? And that brings us back to this question of nature versus nurture. This question of how much of your accomplishment is due to something which is intrinsic and how much is due to your environment was first asked by Sir Francis Galton. Galton was Darwin's cousin. And unlike Darwin, Galton believed that intellectual characteristics were inherited just the same way as physical ones are. And so he was a scientist, he wanted to answer the question, and so he drew up the first questionnaire, and he distributed the questionnaire to the members of the Royal Society. asking him all sorts of personal questions, trying to figure out how much of their accomplishments was due to their environment or intrinsic ability. And at that time, only about a third of the people of the Royal Society had ever gone to college. This is an interesting group of people. And after reading the responses, he concluded that the overwhelming factor was innate ability. And he had this great way of summarizing it, which was, you can't grow great oaks from onion seeds. So,
Can you repeat?
pardon me?
Can you repeat?
You cannot grow great oaks
Yes.
from onion seeds. Well, I think what Feynman did, certainly for me and probably for others, is he reinforced what was already there, made it stronger, gave you more courage. I found it incredible that here's this guy and he's down the hall and he's working like crazy and he's trying to understand things and he's making progress and it's possible. Maybe I should try something. Maybe I should hurry up and get something done. I mean, I'm serious. That is the effect that it has on you. And I think more abstractly, he defines your professional superego. Now, probably the students don't know what a superego is. The superego was a term which was first used by Sigmund Freud. And this must have been at the turn of the last century, end of the 1800s, the beginning of the 1900s. And it is this inner voice that you have that tells you right from wrong, that Freud thought you got primarily from your father. And this professional superego, I think, in my case, I got largely from Feynman. Although the other superego, the one that Freud was talking about, I got at least as much from my mother as my father. Well, before I left Caltech, I went into Feynman's office, and let me just say that the muon was discovered in 1936 by Carl Anderson and his graduate student, Seth Neddermeyer. And when I.I. Rabi first heard of this is the particle that looks exactly like the electron. It's not clear why you need it. It's just heavier. He's reputed to have said in a Chinese restaurant, "Who ordered that?" Well, Feynman had his own way of saying the same thing, which was, why does the muon weigh? And ever since I knew him, in the upper left-hand corner of his blackboard, that was written, why does the muon weigh? And towards the end, it must have been the late 70s or maybe 81, I went to his office and it was erased. And I was shocked. I was tremendously saddened. I thought, well, the Colossus has surrendered. And in fact, he didn't do any additional work in high energy physics as far as I know. All right. Now, there's an enormous amount of hype about Feynman. I mean, we've got the Art and Science Museum, we have all sorts of interviews on television, we have books that he's written, there's books that have been written about him. It's incredible. I mean, he's a real phenomenon that way. But that's not why Feynman is interesting. I mean, there are lots of good performers, there are lots of good comedians. All of that is just bullshit. I mean, just forget it. He's a great man because of his work. And there's a quote by Oscar Wilde, the same Oscar Wilde that Jenny Joy had referred to. And he was supposed to have said to André Gide, "I have put all my genius into my life. I have put only my talent into my works." And for Feynman, it was exactly the other way around. Now, physicists look for universality, the same laws over all space and time, but there's a different universality that exists in all areas where you need creativity. So let me explain, because some people here, the students probably don't know the people that are involved. This relates to two choreographers. Choreographers are people that tell dancers how to dance, just like composers tell musicians what to play. And I think one of the most famous modern choreographers was someone called Martha Graham. There was another choreographer, not as famous, called Agnes de Mille. And de Mille, in 1943, had choreographed a musical called Oklahoma. Okay, that's all you need to know. So in de Mille's biography of the choreographer Martha Graham, she writes, "The greatest thing Graham ever said to me was in 1943 after the opening of Oklahoma, when I suddenly had unexpected flamboyant success for a work I thought was only fairly good." By the way, I saw Oklahoma in 1943. My father took me there. When I suddenly had unexpected flamboyant success for a work that I thought was only fairly good, after years of neglect for work I thought was fine, I was bewildered and worried that my entire scale of values was untrustworthy. I talked to Martha. I remember the conversation well. It was in a Schraft's restaurant over a soda. I confessed that I had a burning desire to be excellent, but no faith that I could be. Martha said to me very quietly, "There is a vitality, a life force, an energy, a quickening that is translated through you into action. And because there is only one of you in all of time, this expression is unique. And if you block it, it will never exist through any other medium, and it will be lost. The world will not have it. It is not your business to determine how good it is, nor how valuable, nor how it compares with other expressions. It is your business to keep it yours clearly and directly, to keep the channel open. You do not even have to believe in yourself or your work. You have to keep yourself open and aware to the urges that motivate you. Keep the channel open." Feynman could have said as much to us. Well, there are those that discover and those that invent, and Feynman will be remembered first and foremost as an inventor. We honor Feynman for the tools he has given us, for his honesty, curiosity, and passion in work. We cherish the time he spent with us. Even after all these years, we miss him dearly. Thank you.